Alright, so in this session we're going to look at the second example. Previously we saw the first example, which was also involving work, and in this one we're going to look at also example. Alright, so this example is as you can see here, this is example 3, where we have a floating ice block which is pushed through a displacement S. Okay, so this ice block has been pushed through a displacement S, 15 meters in the I direction plus 12 meters in the J direction, along a straight embankment by rushing water, which exerts a force F equals 20 newtons I plus 150 newtons J on the block. How much work does the force do on the block during the displacement? So that's our question. Alright, for this kind of a problem where I have a force being pushed through a displacement, and you see what you've been given is just the displacement vector and the force vector. For this kind of problems, or this particular problem, all you have to do is take the dot product of force and displacement. Okay, I'll repeat. For these problems, we will only work with them in this way when you have a force being pushed through a given displacement, like this. When you've been given force and a displacement, then you just take the dot product. So we'll see how this was done. So this is question 3 here. Let's see how it was solved here. Alright, so as you can see here, question 3 there has been solved. Work done is just F dot S. Our F is 210I plus 150J dot 15I plus 12J. So taking the dot product, we just say 210 times 15, we get this value here, and then 150 times 12, we get this value, and then we add, we get our work as it is here, 4950 joules. Alright, and another question is just this one here, which is number 4. We have a particle subjected to a force Fx that varies with position as shown in figure 1, and then you're told to find the work done by the force on the body as it moves from x equals 0 to x equals 5, from x equals 5 to x equals 10, from x equals 10 to x equals 15, and from x equals 0 to x equals 15. So the first part is saying from x equals 0 to x equals 5. Let's look at how the answer was done. For these kind of problems, you solve them by finding the area under a curve for a given region or for a given range. So when you look at this part A here, you have been asked to find the work from x equals 0 to x equals 5. So for this domain, we have to find the area under this curve. So this diagram here is going with this question. So you have to find the area under the curve from 0 to 5 here. Now when you look at this figure here, this is a triangle. So the area under this triangle is what? It's just half base times height. That's how we find the area of a triangle. So we say half, our base is just from 0 to 5. So half base, this base here, height is just from this point all the way to that point. So height is 3, base is 5. When you look at the solution here, you find that the area under the curve is just half base times height, which is what we've just talked about. The base is 5, the height is 3. According to this diagram, the base is just from 0 to 5, and the height is from 0 to 3. So that is how we find the work if you've been given a force displacement diagram. So this is just a force displacement diagram. We're talking about how force is being related to the displacement. So whenever you've been given a force displacement diagram like this, or it may not even look like this, it can look in a different way. For as long as you've been given a force displacement diagram and you are told to calculate the work, you just have to find the area under the entire curve. Alright, part B is just talking about the work done from 5 to 10, which is just the area under this part here, which is a rectangle. From 5 to 10 we have this part, a rectangle, and we know area of a rectangle is just L times B, or base times height. It's just base times height, right? Base times height. So the base is the distance from here to here, which is 5, times the distance from here to here, which is 3. So it will just be 5 times 3, as it's been done here. 5 times 3 we get 15 joules. That's part B. Part C is talking about the area from let's see it. Here is part C, from x equals 10 to x equals 15. From x equals 10 to x equals 15 we have another triangle, so we find the area of this triangle, which is half base times height. So it will come back as 7.5, just like in part A. So 7.5. And part D is just talking about the area under the entire curve, which is just the sum of these individual areas. So when you add this area, and this area, we get the final area, which gives us the total work done. So when you add this plus this plus this, you get 30 joules. Alright, that's how it is done. And now we can also look at a question which is combining many parts of what we've just done. Let's look at number 5. Number 5 is a particle of mass m which moves in the xy plane so that its position vector is r equals a cos omega I plus b sine omega j. So this is the position vector, or the position vector is over this particle as it moves along this ellipse. The position vector is defined by this expression here, where a, b and omega are positive constants. So a, b and this omega are positive constants, and a is greater than b. Yes, so we've been given a is greater than b. As you can see from this diagram here, you can see the distance of this a here, it is greater than this distance of b here, as shown in figure 2 here. And okay, let's see now what is here. Our first question is to find the kinetic energy of the particle at points A and B. So you see, we're already now on this part. When you look at these notes, there was a part where we talked about the kinetic energy. Where is it? Okay, we saw the here kinetic energy is just half mv squared. So let's now go back to our question. Now looking at this question here, it is saying find the kinetic energy of the particle at points A and B. So at point A, for you to find the kinetic energy, you have to look carefully and note something. At point A, this is point A here. At point A, what do you think the angle is here? The angle for this particle, the position of the particle when this particle moves from this point where it is m, this particle is m, it has mass m. What if it was at point A? What angle would this position make with this axis here? And it is clear that the angle it would make is 0, meaning that at A, omega t is 0. Yes, that's what it would mean. It would mean that at A, omega t is 0. Okay, 0 degrees or 0 radians. So let's just keep it in radians. So at point A, omega t is 0 radians, and at point B, when you look at this elevation from this point to this point, this position will make an angle of what? 90, right? From A all the way to B, this position vector will make an angle of 90 degrees, and 90 degrees is just pi over 2. Alright, so let's get to work now and find the kinetic energy at point A and B. Let's solve for part A. So now look at how question 5 has been solved. We're saying that kinetic energy is given by half mv squared, yes, but we don't know v. Alright, yes, we don't know v here in this case. We don't know velocity v. Remember, this v here is a scalar. Energy is a scalar. That's why we have this v as a scalar. So we're saying that now, since we don't know what v is, we have to find it. We know that from vectors that v is equal to dr over dt. Okay, and we know what r is. We know what r is. It's been given here. R is just this equation here. This is r. Okay, so we know, and now we're trying to find the r over dt. So we start with the r over dt, which is equal to d over dt over r. This is our r inside here. The r we have been given is this here. So taking the r over dt, we'll find that v is equal to this expression here. Here we're just differentiating this expression with respect to t. When you differentiate cos omega t here, you will get minus omega a sine omega ti plus omega b cos omega tj. We get this. Okay, now what we have found as v is a vector for this case, right? But now we want to convert it to a scalar, which is just a v without a arrow on top. So now for us to have a v without an arrow on top, we have to take the dot product of these two vectors, right? So we have to take these dot products, and when we take the dot product of this vector with itself, we'll have v squared. Okay, so v dot v gives v squared. That's something you should know. And here it's been given, as you can see, v dot v, right? And we've got our v squared here. So in other cases, we found this v here, this v squared, we found it, which is here. We've literally found v squared here. So we're taking this v has been put in parentheses here, dot itself here, it's repeating. But now I'm sure you all know how to take the dot product, right? So when you take this expression times this expression, we're getting this expression. And then when you take this expression times this expression, we're getting this expression, right? Okay, so this is our v squared here. Simple, right? This is our v squared, which is a scalar. Alright, we want it to be a scalar because we know that energy is always a scalar quantity, as you can see here in this expression. Okay, so now since we have our v squared, which is this, taking back this expression into the formula for kinetic energy, we'll have half mv squared, right? And putting back the v squared in here, we'll get half m v squared here. So this is v squared here, okay, at point A. Okay, so that's at point A we have our kinetic energy. So let's say this is the general equation, right? This is the general equation for our kinetic energy, and at point A, omega t is equal to 0. So we're looking now at point A. We're trying to find the kinetic energy at point A from this general expression for kinetic energy for a particular question. So at point A, omega t is equal to 0. When you look at this diagram again, we'll go back here. So when you see at point A, what will be this angle when the particle is at point A? What do you think this angle will be? It will just be 0. Yeah, and when it is 0, we're going to have sine omega t equal to 0, because we'll replace omega t with 0 here, and it will become sine 0. Sine 0 will be 0, right? And what will happen to cos omega t, right? Cos omega t, this will be the same as cos 0. Cos 0 is 1. That's why we're getting 1 here, because omega t is 0. When we replace in here, we'll have cos 0 being 1. So now when we substitute these values for sine omega t in here, have you seen sine omega t there as 0? We take it there, plus omega squared v squared cos squared omega t. Alright, so now cos omega t is 1, right? So this cos omega t will be 1. Here it is just squared, but there is no difference. Okay, so when you take this omega t and substitute in this expression here, we'll have a 1, and this whole part here will vanish. This whole part will vanish because it will become 0 according to what we've known here. Okay, and we're saying that hence the kinetic energy at A will be half m omega squared b squared. Okay, half m omega squared b squared. That will be the kinetic energy at A. Alright, I hope you've understood what we've done here, because we've simply eliminated this thing, because this thing is turning out to be 0 at point A, and this whole thing here is turning out to be 1. So we'll only be left with omega squared b squared. So that is what we have at point A, half m omega squared b squared, and at point B we'll have omega t being equal to pi over 2. This is what I simply explained earlier. Omega t is pi over 2 at point B. When you look at point B is here, right? And when you look at a particle moving from this point to this point, what do you think the angle it makes? It makes an angle of 90. Moving from this point to this point, it makes an angle of 90, and an angle of 19 radians is just pi over 2. That's why we said this angle omega t will be equal to pi over 2. Okay, so the angle will be pi over 2 there, and as we have said here, at point B omega t equals pi over 2. Hence sine omega t will be 1. This is the same as sine pi over 2 is 1, right? Sine 90 is 1. Sine pi over 2 is 1. And what will happen to cos omega t? Cos omega t, which is cos 90. Cos 90 is 0. So when we substitute for these values in this general expression for kinetic energy, we find that this expression sine omega t, just this part here, sine squared omega t, it will become 1, and will remain with omega squared a squared on this part. And here we're saying that plus omega squared b squared cos squared omega t. Now in this second part of the expression, this one here, when you replace with cos omega t, which has been found to be 0, we'll find that this whole expression will vanish, right? This whole expression will vanish to 0. So if this thing vanishes, and this thing, this sine squared omega t becomes 1, as we have found here, rather as we have found here, yes, as we have found here, this sine omega t will become 1, will just remain with half m omega squared a squared here. Will just remain with half m omega squared a squared. As you can see here, kinetic energy at B will be equal to half m omega squared a squared, and that is our kinetic energy at B. Okay, alright, so let's continue for part B. For part B, which is talking about part B, let's see what part B is. Part B is just saying find the work done by the force field in moving the particle from A to B. Alright, so for this part, let's solve it in the next video. Part B is just saying find the work done by the force field in moving the particle from A to B. From A to B. The work done now is what we're calculating. Alright, so I'll see you in the next video for this part B.